Good morning. Today we're going to demonstrate how you can take a snapshot of a die and convert it into what we call a die pad netlist. The XY coordinates of each die pad that can be used then for creating a wire bonding document. Let's start from the beginning with what the image looks like. I've opened the TIFF bitmap in Adobe Photoshop. I see that the pads are considerably different color than the rest of the die image. We need a distinct differentiation between the pads and everything else if we're going to be able to extract them. The first thing I'm going to do is to clip this to the extents of the die itself and get rid of anything that's outside. And we can use the cropping tool here. And we'll just pull this down here. And we'll pull this a little over there, and we'll pull this up just a tad, and then this one over here to the right. All right, and that's our image. Now, if we look at the image that we received, we see that it's actually still a color image, 8 bits per channel, and we really are going to get to a monochrome image. The first thing I could do is to, say, zoom in on this area. And then I could go into the threshold filter, and that lets me set a value for converting from gray into black and white. And as you see, as I slide it one way, I can get more black, more white. This is already a very high contrast image, so I'm going to stretch it like this. Each time you do this, you want to adjust that, and it will affect the size of your pad slightly as things move in and move out there. I think that's a good value, so I'll just click OK. And now I'm going to go to image mode, and we'll go first to grayscale. And we're just going to discard the color information. Now we're going to go image mode a second time to bitmap. This doesn't really matter here, the DPI. We're going to set that independently. And we'll use 50% threshold. Click OK. Now we've got a bitmap image. If we go image mode, it says bitmap, which is all zeros and ones. We're going to proceed from there. Now the other thing we're going to do, because of the way TIFF to GDS works, we want this black and this white. So we're going to go to image, and I think we can go to adjustments, and we're going to invert it. And there we go. So I'm going to say file, save as, let's just call it monochrome, and invert. And we'll save that. And we don't need any compression. Boom. So now we've got the black and white file that TIFF to GDS needs. Now that we've prepared our TIFF file, we're going to use the TIFFDeMevis program to convert that into GDS2. The settings are to select GDS2 as the output, to check the union box. This is the maximum amount of points per boundary allowed in GDS2. We'll set it to that max. Pixel size. Now this is what's going to determine the size of each pixel in GDS2, and we computed that it was this value. So I can just put that in there. And then the output file will go to the same directory, and it'll be called monoinvert.gds. So all we have to do is click translate now, and it'll take a few seconds to do that. Now it's doing the Boolean, and we see that it says translation successful. Let's look at that output file. We've brought up the GDS2 in our viewer, quick view. I'm going to zoom in, say, over here on this side, and have a look at what we've got here. If you look right here at one of these squares and you click on it for information, you'll see that it's a polygon, and it has what we call a cut line to account for that little die probe mark in the middle, and it's separated from everything else. Let's see how big they are. We could go to our ruler and we could actually measure them roughly from corner to corner. And this is telling me they're about 95, 98. There's a certain amount of noise, and so we're never going to know the exact size, but here's 95, 96. Let's move this up here and measure that. See if we can measure there. That one's 94, 97. So it seems like we have about 3 microns of noise. However, it's likely that the center point is half of the noise, so we're probably accurate to within 1 to 1.5, maybe 2 microns at the worst. Now we do have one strange pad here. this octagon. And we will have to be careful when we do our filtering not to knock this guy out with a filter rule that passes these square guys. Our next step is to remove all the noise so that all we really have are the pads. And we'll use GDSFILT to do that. All right, now that we have our GDS2 file, we want to remove everything but the die pads. And we'll use a program called GDSFILT to do that. So let's start by selecting our GDS2 file. And this is the one we're going to select here. We don't need to select the structure because there's only one. We don't need to do anything special on the configuration. We don't even need these options. We want to use the polygon filtering function. What I typically do is set some minimum and maximum extents for the polygons, and that will remove polygons that are less than 75 microns in extents and any that are more than 120. So anything that's small will get removed, anything that's large will get removed. In terms of height to width ratios, we're going to remove anything that exceeds 1.3. That will get rid of anything that's long, and horizontal is anything that's vertical. Since our pads are square, that will remove the ones that aren't square. Finally, this determines the ratio of the bounding box to the actual area contained by the polygon. Because of the cutouts in the middle due to the die probe, I'm going to keep that very conservative, and I don't want it really to do any work. I'm simply saying any polygons that have more than 1,500 vertices probably are not our simple pads. So with this criteria, I'll click OK, and then we will run a translate. We'll call this, let's just call it filtered. And save. We're done. So now let's look at what our output looks like. And there we are. It looks like we're in good shape. We have all of our die pads, and we got rid of all the unwanted ones.